So what happens when a swinging sandbag smashes into a cart? Does it bounce? Does it stick? And why does the cart slide to a stop? Today, we're diving into the wild world of inelastic collisions and fiction, where physics just gets fascinating. Recently, we've got a sandbag, and we've got a plastic cart, and some paper to track the action. The sandbag swings down like a pendulum, smacks into the cart, and we measure how far the cart slides. Simple setup, big experience. Let's get to the fun part. Releasing the sandbag, watch it as it swings down, collides with the cart, and sends it sliding. But here's the catch. If the cart swerves and it's a no-go, we need a clean straight slides for good data, right? After a few tries, here's a perfect try. So, now let's break it down. As the sandbag falls, its potential energy turns into kinetic energy. Physics explains. At the collision, momentum is conserved. Not so much. Some of it turns into friction. Other parts of it turn into sound, thermal energy, any of other stuff. So here's the math behind this.
Let all the vertical distance represented by the change in t. So that the gravitational potential energy is converted into kinetic energy represented by initial B equals the square root of 2g times change in t. Then the momentum is conserved when the sandbag mass mv strikes the cart of mass mc. The two stick together. Momentum in the horizontal direction therefore is conserved. And that can be represented by transforming equation 2 into v1 equals mv over mv plus mc multiplied by the whole fraction by v, which is initial velocity. Then in step 3, the work done against friction against the collision that combines system stress and traveling at distance s along the table. And all the kinetic energy right after the collision is dissipated from effective friction, which shall be represented by the equation of 1/2 mv plus mc multiplied by v1 squared, which will equal the force of friction times distance s, with the frictional force given by force of friction equals mu k times mass of cars times gravity. It is possible to combine all these equations to relate the drop height changes to the distance s traveled after impact on the soul for mu k. So starting with equation 1 and 2, we have v1 equals mv over mv plus mc square root of 2g change t. Now we substitute v1 into equation 2 to end up with 1/2 mv plus mc, all of it multiplied by mv over mv plus mc, which was multiplied by the square root of 2g times change in t, and the overall equation is squared to the power 2, which will give us mu k mc times gravity times distance s traveled. Square the expression inside the bracket and we take away the square root, cancel the 2's, and we end up with an equation of mv, the mass of the balloon squared, over mass of the balloon plus mass of the cart, all the fraction multiplied by gravity multiplied by the change in t, which will equal mu k times the mass of the cart times gravity times distance s. Now we cancel g, assuming g does not equal 0, and solve for mu k. Therefore, mu k would equal the mass of the balloon squared times the change in t over the mass of the cart times the mass of the balloon plus the mass of the cart times the change in t. This equation tells us that if we know the drop height change in t, which is the difference between initial z minus final z, the mass is mv and mc, and measure the distance s that the cart travels after the collision, then we can compute the friction coefficient mu k. So given that our height is 69.5, the mass of the balloon is 69.5 centimeters, the mass of the balloon is 86 grams, and the mass of the cart is 69 grams, we can start computing. And this is the resulting data. Therefore, the average is approximately 0.843, which is what mu k is.